Here we're given a graph of a function f of x without its equation, so we're just given the picture, and we're being asked to graph the function h of x, which is a transformation of that. It's f of 1/2 x. So the difference from f of x to f of 1/2 x is that we have that multiple of 1/2 in there. Anytime we have a multiple, that's going to be a stretch or shrink. Since it's a multiple directly on the x, it's affecting the x coordinates, it's going to be a horizontal stretch or shrink. Now intuitively we would think that multiplying something by 1/2 would make it smaller, and therefore we'd want to say it's a shrink, but the horizontal transformations work kind of opposite of our intuition. This is actually a horizontal stretch. So what we mean by a horizontal stretch is that any points on the y-axis are going to be fixed, and then everything else is going to get pulled away from the y-axis. So these points that are to the right of the y-axis are going to get pulled further away to the right, and these points on the left of the y-axis are going to get pulled further away to the left. And because of our multiple being 1/2 here, they're going to get pulled twice as far away. So we could say that this is a horizontal stretch by a factor of 2. Okay, so what we're going to do then is take each of our points. Let's look at this point -2, 0 to start. Right now it is currently 2 units away from the y-axis, so we're going to stretch it further away. So we're going to double that distance and go to 4 units away. So that results essentially in just multiplying our x-coordinate by 2. -2 times 2 would put us at -4, and I'm going to plot that point over here. Okay, so we're going to take each of these points that's labeled and multiply the x-coordinate by 2. So in this next point, 0, 3, 0 times 2 is still 0, so that's still at 0, 3. And then just connecting those two dots effectively stretches that entire line segment. Okay, we'll go ahead and look at the rest of our points here. 2, 0, so 2 times 2 would be 4. And then we'd have 4, -3, so that's 8, -3. And then we'd end up at 12, 0, which is going to go a little bit off of my chart there. That would be out at 12, so there's 11 and then 12. And so we'll go ahead and connect those dots in the same way that they're connected in that original function. And we can see that the way this graph is different from the original is that it's been elongated horizontally. Now vertically it still goes from a lowest point of -3 to a highest point of 3. And that's because we didn't stretch it or shrink it vertically, we only stretched it out horizontally. We pulled things away from the y-axis. So to kind of verify that we have done things correctly, as we might be tempted when we see that 1/2 to multiply our x-coordinates by 1/2 instead of by 2, let's go ahead and pick one of the points that we landed on, and I'll go ahead and choose this point here, 8, -3. Since that point is on the graph of our function h of x, what we are saying there is that h of h of 8 is -3. I don't have an equation to plug that into to verify, but I can go back and plug it into our formula here involving the function f to make sure that things are matching up. So that formula says h of x equals f of 1/2 x. So h of 8 would be f of 1/2 times 8. Half of 8 is 4. So I'm looking for f of 4. F of 4 is telling me to look at my graph of f and find the y-coordinate when x is 4. So that point's labeled right here. That has an x-coordinate of 4, and the y-coordinate there is -3. So that's what we were expecting. We wanted h of 8 to be equal to -3, and it is. And so that verifies that we have applied the correct transformation and generated the correct graph.